Another place where we apply trigonometry is when working with vectors. So first we'll talk about what a vector is, then we'll talk about expressing quantities as vectors, so the different notations, how we operate with vectors, and then we'll do some applications as well. So first, what is a vector? Well, a vector is a quantity that has both a magnitude and a direction, versus a scalar would be a quantity that just has a magnitude but no direction. So a good example of the difference between those things would be speed versus velocity. Velocity can be expressed as a vector because we state the direction of the speed, right? And so then we can state that as a vector, whereas speed is just how fast you're going without any direction, so that's a scalar. So geometrically, we would express a vector using an arrow, and the arrow denotes the direction of the vector, and the length of the line segment represents the magnitude of the vector. So if I draw, say this is vector v, and I use this little arrow above v to show that it's a vector, then maybe vector W goes the same direction, but this longer line segment means that this would have a larger magnitude. And the thing about vectors is it doesn't matter where you draw it. As long as it's the same direction and same length, then if I put V over here, well, I guess I write this down here. Sorry, getting ahead of myself. Those are equivalent vectors. So if I have V up here, if I'm trying to draw this the same length and the same direction, I can draw V down here. Those are equivalent vectors. They don't have to be in the same location, so you can translate them anywhere. Let's see, what else do I want to say? Oh, some notation stuff here. So when I want to talk about the magnitude of these vectors, the notation for representing that would be, we use these double bars. So you can also just use like absolute value symbol, but I usually like to use a double bar. So this represents the magnitude of V. And if we want to represent the opposite direction, we would draw the same length line segment but put the arrow on the other end. So I might draw this vector, and that's negative V. And the direction piece of it, we're going to deal with angles, so that's where trigonometry is going to come in. So if you think about measuring from the horizontal, I'm trying, these angles should be the same. We'll get to that later. Alright, so all of these vectors here are equivalent. I can draw V wherever I want in the plane, and it's an equivalent vector. Alright, when we add vectors, let's just say we have two vectors geometrically here. We're going to do this, so let's use V again, and then maybe this is vector U. So what we do is we take V, and I'm trying to draw it with the same angle here. So here's V, and then you take U and put its end at the tip of vector V. Try to make it the same angle as I drew here. So here's U and the same length. Then U plus V is the length of starting at the initial point of vector V to the terminal point of vector U. So this, let me move where I wrote my V. So here's V. This would be U plus V. Then let's talk about scalar multiples of vectors. So when we take a multiple of a vector, like say I have vector V here, and I want to, if I make it 10 times as long, then I'm multiplying by a scalar, the scalar 10, and it will, I'll just draw this 10 times as long, and that will be 10v. Maybe I'll do 5 because I want to make it somewhat accurate. So here's 1, 2, 3, 4, let's just say that's 5. So this is vector 5v. And if this is 1 unit long, it could be anything, but whatever that number is, you multiply it times 5. So 5 times v has magnitude. Notice we use absolute value symbol here because a is a real number, it's not a vector. Okay, so this is like our 5 here. Just if that's a negative 5v, it's just going to go in the opposite direction. But magnitude is always a positive number, so you would take absolute value. So the magnitude here would be 5. And whatever the length of v is. I just made v a length of 1, right? If that's a length of 2, then of course this would have a magnitude of 10 instead. Okay, and again, if it's negative, it just goes the opposite direction. All right, let's see. Oh, and subtraction. We talked about addition. So now if we have subtraction, I guess I used u and v here. So let's say this is u, and maybe this is v. Then let me draw u again. So here's u. And then v, when we add v, it goes here, right? I'm trying to make this the same angle so it's parallel to this. So this is u plus v. We already did that. What we do for u minus v is think of this as u plus negative v. So at the tip of u, instead of drawing v in the same direction it went before, you go in the opposite direction. So this is negative v. And so this, again, starting from the initial point of u, this is vector u minus v. So when you add vectors or subtract vectors, you get another vector, right? And u minus v is here, and here's u plus v. In fact, if I draw the picture a little differently, because we can translate vectors anywhere in the plane, the following is true. If you take two vectors like u plus v, I'll draw it here, or u and v, I should say. So here's u, and here's v. And you draw a parallelogram. The long diagonal is u plus v, and the short diagonal is u minus v. Whoa, how come that looks so far off? Wait, what if I do u, v? Well, this would be better. I should have drew this out probably in the plane. It would look better. So here's u plus v, and then u. Oh, that looks kind of off, doesn't it? It should look like this one. Well, for one thing, my parallelogram doesn't really look like a parallelogram. Let me try to redraw it. Sorry. I don't want to waste a lot of time on this. Okay, try again. Make this. Maybe I'll just take a new drawing so I don't have to make it exactly like this. All right, so say we have, well, okay. I guess I still want to use this. Let's just do this. So here's u. Here's negative v. So just draw this parallelogram. Let's do it this way. And then see this other diagonal here is the same as u plus v. That probably looks a little better. And then, so one diagonal will be, the shorter diagonal is the difference, and the longer one is the sum. Okay. okay? Let's move on. I mean, I'm not going to test you on that anyway, so I don't want to spend a lot of time on it, but I just wanted to mention it. That's what actually ends up happening. Okay, well, let's talk about standard position. I mentioned that like when we talk about the direction, we'll refer to the angle. So I might say, you know, if I put the horizontal here, maybe this is 25 degrees, right, from the horizontal. So there's different ways I could state the direction. What, you know, I might say vector u represents the speed of a runner. He's running 6 miles per hour and running due north, right? I give this, the direction is due north. We need to standardize that. So what we're going to do, you know, and again, these vectors, they can translate anywhere. We're going to draw them in standard position that we all have the same point of view, okay? So standard position, just like we draw our angles when we, you know, derived our trigonometry functions and talked about the unit circle and all that sort of thing. We'll translate these into the plane, and then vector v, we can refer to its components here. We call these the components, and those will actually be the same as the coordinates of the ordered pair that lies at the tip of the vector. So I should have left a little more room for a drawing, but let's just say this is point A, B, and this is vector v. Then v is equal to, so this notation represents a vector. We refer to the horizontal and the vertical component, and that's you know, how far to the right you would go is the horizontal component, and how far up you would go is the vertical component. So it's just like plotting a point in the plane. Then we can talk about you know, the angle measured from the positive x-axis, just like we always do. So when I say due north, I would just say, well, theta is 90 degrees or theta is pi over 2. If it's due west, then theta is 80 or 180 degrees or pi, depending on if you're using radians or degrees, right? So we put it in standard position so that we're all looking from the same point of view and measuring from the same place. But again, the vectors can really be drawn anywhere. Vector v doesn't have to be drawn here. It can be drawn way over here, right? But it gives us a frame of reference. So anywhere the vector is, we're going to put its initial point at the origin. If the vector is given in terms of two other points, so maybe, you know, this vector here, we want to get it, translate it, so its initial point is down here. So we're given the initial point and the terminal point. Then all we need to do is subtract corresponding components to get v in standard position. In other words, take, and it's always from the terminal minus initial. So take the ending point minus the beginning point. And so you'd have your you know, Q1 minus P1 for your first component and Q2 minus P2 for your second. So once that's in standard position, we refer to it as a position vector. So position vectors are in standard position. That means their initial point is at the origin, okay? And two position vectors are equal if and only if their components are equal. And remember, the components is kind of like the ordered pair, right? But it's not an ordered pair. We're thinking about this differently. The vector has the magnitude, which is the length of the vector, and then the direction, which we can refer to as an angle. Okay, so one thing I forgot to mention, and I should talk about it, is notice in my, like how I have this typed up, I don't have an arrow over u or an arrow over v, but every time I write it down I put an arrow. And that's just because in type I can make this bold and it's clear that it's a vector. But when I write this, it's not clear it's a vector unless I put an arrow over it. So you should get used to that practice when you're using a letter to represent a vector. Put an arrow over it so that you don't mistake it for just a a variable that would, you know, just be a scalar. We want to be clear that these are vectors. So just use an arrow. That makes it clear. But in type, usually it's just a bold, you know, letter, and then it's clear that it's a vector. And again, this means an ordered pair, and this, when you make these angled like that, then you know it's a vector you're referring to. Because those are different things. You don't want to think of them as the same. Okay. Some other things, 0 vector here. So if I were writing this 0, obviously if I had just wrote that, it looks like the number 0, but this changes it. Now I know we're talking about a vector with component 0, 0. And so how do we find the length of the vector? That's its magnitude. Well, we can just use the Pythagorean theorem to derive this formula, right? We know that the length here, that's just like finding r when we talked about our definition of our trig functions. And that, of course, that's just the square root of a squared plus b squared. Derive that with the Pythagorean theorem. I'm not going to spend time on that because you should be used to that formula by now. All right, and then sometimes we refer to unit vectors. A unit vector is a vector of length 1. Okay, so that's pretty easy. Just leave it at that. Okay, so when I say find the magnitude of vector u, so this vector, the tip lies in the second quadrant, right? If I were to graph u, I'd go back 3, up 2. So when I want the magnitude of u, I'm really just looking for the length of this line segment, and that will be, whoops, I need to put bars around here, the square root of -3 squared plus 2 squared. 9 plus 4 is 13, so the square root of 13. So that, you know, it's easy to confuse the concepts because we're doing a lot of things the same, you know, the same things we did previously, but keep in mind we're applying them in a different way, so it's not exactly the same. So I should move that up. All right, so here we have a vector with its initial point at -2, 5 and its terminal point at 3, -3. We want to find the components of the vector. So that means we want to find the position vector. And I'll draw, and then put a graph here, but let's just draw a little picture of what's actually going on. So -2, 5 would be, that's the initial point. And then the terminal point is 3, -3 right here. So what we want to do is find the components, and we're calling this vector u, so that these numbers will end up, you know, if you translate this to standard position, it's going to be parallel and the same length. So this, the components will be whatever this ordered pair is if you take this and translate it over here. So it's very important you get the order of subtraction correct, otherwise it's going to go in the opposite direction. So terminal minus initial. So first the x coordinates of the points, so 3 minus -2, right? And then -3 minus 5. And that gives us 5, -8, which seems reasonable. See, that's the ordered pair here, right? We'd go over, my picture is not the best because I'm doing it by hand, but if I had a grid here, I could get a more, a better picture probably, but you could just count, you know, how far over do you go? What's the, you know, this is 5 units over to here and then 8 units down. And then you'd get an equivalent vector. So here's, you know, you can describe the vector, but this is how you write it in with the notation, vector notation. Whenever you use this notation, it's a position vector. All right, so let's talk about operations, because we talked about addition and subtraction geometrically, but now if we have sorry, see, way too much. If we have position vectors, we can actually do some operations. So if u is this position vector and v is this position vector, the resultant vector from the addition will just be adding up the corresponding components. And we can look at that when we do some numbers and show that that works, except this should be a B1. So add the first components and then add the second components. And then if it's subtraction, you just subtract the components, go in the order that's here. So if U is first, then you put in A1 first, and then A2 minus B2. If this is V minus U, you'd flip those around. And then scalar multiplication. If A1, B1 are the components of U, then to take it times C, you're just going to multiply each component times C. It becomes that much bigger, in other words. All right, so these are really easy to do. It's just adding and subtracting and multiplying. So this we could write 3, negative 4, plus 2, 7. So you just add 3 plus 2 is 5. Negative 4 plus 7 is 3. And if you think about the xy plane here, so we have 3, negative 4. That is vector U. Vector V is 2, 7. Here's V. Here's U. And then 5, 3 is here. Right? So this is U plus V. So if you took this and put it at the tip here, oops, I gotta go make sure it's parallel, and then go in the same length, take, from here to here, see this is the same length and it's parallel to U plus V. It's just this, oh, wait a minute. This is at the initial. This picture's no good. Sorry. This actually ends up at the tip here because this is already in standard position. See, this is V. So remember, this V doesn't have to be in standard position. When you add it here, and that ends up at the position vector U plus V. Okay. So now when we subtract, it's just subtracting components. So, whoops. What did I do that for? So 3 minus 2 is 1. Negative 4 minus 7 is negative 11. So this would be at 1, negative 11 down here. And again, you could draw V going this way, and you'd see that you end up down here. This would be U minus V. So the geometric stuff we looked at before still all works here. We just now have a way to refer to where the tip of that vector is. Okay, I don't want to spend too much time on this, so let's keep moving. All right, negative 3U, we just take negative 3 times our vector, which is 3, negative 4, so we get negative 9, 12. This vector goes in the opposite direction of the original U because the scalar is a negative. 2U minus 5V, we would take 2 times 3, negative 4, minus 5 times, 2, 7. And so 2 times 3 is 6. And then minus 5 times 2 is negative 10. 2 times negative 4 is negative 8. Minus 5 times 7 is negative 35. So we end up with negative 4, negative 43 is our answer. All right, so anything like this should be really easy to calculate. Okay, so now properties of vectors. So I have this whole list of properties of vectors. These correspond kind of to our properties of real numbers, right? Like addition is commutative, multiplication is commutative. Addition and multiplication are associative, those sorts of properties. So we, are looking at these in terms of vectors now. So this first one is saying that vector addition is commutative. You can add in any order. That shouldn't be a surprise. The second one is saying vector addition is associative. It doesn't matter if I add these two first and then add the result to that, or add these two first and add this to the result. So this is the associative property. This here, because this is bold, this is a zero vector. So you can't add a vector to a scalar. When you're adding, you have to be adding vectors because there's two components. So the zero vector is the additive identity. That's what this one is saying. This one is saying that negative u is the additive inverse of vector u. So this is additive inverses. This one is just saying the magnitude of c times u is the same as the absolute value of the real number c times the magnitude of u. I don't really have a name for that one, but we could prove that pretty easily. This one is, well, actually these two are distributive properties. If you add u and v and then take a multiple times a scalar c here, that's the same as if we took those separately times c and then added the results. And then this is saying if we add two scalars and then multiply it by our vector, we could also just take each of these scalars separately times u and add up the results, and we get the same answer. So these are two different types of distributive properties. And this one is an associative property again. We've got scalars here, so c times d, and then times u, or we could do d times u and then multiply it through by c, etc. And those would all be equal. It doesn't matter when we multiply by the scalar. Okay, and then this one here is a scalar. It's saying that 1 is an identity for scalars. So 1 times vector u will give us vector u. And then here, this 0 is different here than the one up here because this is not in bold. This is just the scalar 0. You take it times the vector u, and you're going to get the vector 0. So the bold, these are vectors. Okay, so we're not going to really do anything with that other than make note of them, and we can apply them as needed. All right, moving on to unit vectors. Again, a unit vector is a vector of length 1. So we can take any vector and create a unit vector that goes in the same direction, as long as it's not the 0 vector. So, for example, vector v, this is not a unit vector. The magnitude of v is the square root of 3 squared plus negative 7 squared. So 9 plus 49 is 58, so that's the square root of 58. But we can create a unit vector by taking our vector v times the reciprocal of this. So 1 over the magnitude of v times vector v is 1 over the square root of 58 times 3 negative 7. I did that again. It's not an interval. Okay, so this is 3 square root of 58 and then the second component is negative 7 square root of 58. And how would we check our work? We'll make sure that the magnitude of this resultant vector here, result, is 1. So check the magnitude of vector 1 over v times v, right? Because we got a vector for an answer, so we can take its magnitude, would be the square root of 3 over square root of 58 squared plus negative 7 over square root of 58 squared, square root of 9 over 58 plus 49 over 58 is the square root of 1, which is 1. So we do in fact have a unit vector now. So this will always work. We only showed it for one example, but this always works. So here's a formula for a unit vector. Alright, now we're going to change notation a little, which might be confusing. But this is the preferred notation in physics, so we are going to introduce that here. So in the vector 1, 0 is a unit vector. If we put this in standard position, right, this is 1. This is vector I. So again, in type, this is just a dot, but when I draw this, I'm going to put an arrow on the top. We don't want to confuse that with the imaginary number I. And then j is 0, 1. So j goes up the y-axis, I goes to the right on the x-axis. These are unit vectors, and so we change our notation. Something like negative 2, 3 is the same as negative 2 times 1, 0 plus 3 times 0, 1. I don't know why I keep doing that. So negative 2 times 1 plus 3 times 0, right, is negative 2. And then negative 2 times 0 is 0, plus 3 times 1 is 3. So these are equal. And then this is vector I, and this is vector j. And so we get negative 2i plus 3j. So these are vectors. This is a vector. And it takes some getting used to, but every vector can be expressed in ij notation. You just take the first component times I and add it to the second component times j. It's really easy to switch back and forth. So here's the result, and of course we can prove that these are equal, like we just showed these are equal here. And then the terminology is the same. A is still the horizontal component, B is still the vertical component. Okay, so that everything else is the same. It's just a new way of writing down the vector. So if V is the vector with initial point 5, negative 4 and terminal point negative 2, 8, right, V is a linear combination of I and J. So linear combination, this is a linear combination. You take, a multiple of I, a multiple of J, and add them up. So then, in this case, vector V will equal, so you take terminal minus initial, and then take that times vector I, plus, sorry, make sure I got them right here, and then 8 minus negative 4, difference of the second components, times vector J. And so this is negative 7I plus 12j. So we did a problem like this. Let me see if I can find it. Well, I guess it was the second page, right? It's basically the same problem. We just used a different notation. This here was what, they're different numbers of course, but that's what we did here. Rather than put it here, we just put it in front of I. And then this Oh, there I did it again. I just want to use interval notation. I like IJ notation better, because, well, since I have this problem today, that would be one reason, but I don't know, I just prefer it. Okay, so then this here would go in front of J. So basically the same problem, just using a different notation. And then when we do vector addition, subtraction, scalar multiplication, so u plus v, it's just like adding like terms. Negative 4i plus I, oops, sorry, and then plus, and you don't have to write this down because it's so easy, you can just do it all in your head, but I'm going to write it down this first time. Negative 3j minus 6j plus a negative 6, right? So minus 6j. So this is negative 3i minus 9j. And then 2u minus 3v, just 2 times negative 4i minus 3j minus 3 times I minus 6j. Whoops. I want to make sure I put my arrows there. On the IJ, you don't have to use the arrows. Sometimes I do drop them. I just want to be careful because with the I, it can look like the imaginary number I. And when we get to, not the next section, but the next one, we're going to work with imaginary numbers. And I don't want you to confuse those concepts because we use a lot of the same elements again of trigonometry once we get there. It's easy to confuse the ideas. So just be careful. But you can, you know, like here, I could just do 7i plus 12j. If I decide to do this, just make sure you don't write your I like that. Like I would reserve this for imaginary number I. And then this for the vector. Okay, let's finish this up here. So negative 8i minus 3i is negative 8i. And then negative 6j plus 18j is plus 12j. Okay. Find the unit vector that has the same direction as u. So we already did a problem like this. It's just using a different notation. We need to find 1 over the magnitude of u and then multiply it times u. So this is 1 over the square root, and the components are just the coefficients. Negative 4 squared plus 3 squared times negative 4i plus 3j. Again, and I could put arrows here if I want. Alright, so 16 plus 9 is 25. Square root of 25 is 5, so that's 1/5 times negative 4i plus 3j. So negative 4/5 I plus 3/5 j. I'm just going to drop the arrows. It gets tedious after a while. But with the other types, for sure, make sure you're using arrows. Okay. I'm on the screen. Okay, good. All right. This next part gets a little long, so I think it's a good time to take a break. So now here's where the trigonometry is going to come in. When we deal with, we know how to do the magnitude, but then what about the direction? And what was I going to say? I'm sorry, I said that wrong. Let me go back. What we're going to do now is, like, this tells us where the vector is, and then we can find the magnitude, right? The direction part we can find using trigonometry. We'll talk about that. But what this is actually doing is we are just told, like, okay, this vector has magnitude 5, its direction is 30 degrees. Can we find the components? That's our objective here. So this is our theorem. We'll talk more about that in the next video.